Coming up on today's show, moisture absorption impacts the properties of resin as well as the actual processing parameters. Let's understand what's really going on with moisture and resins. Welcome to That Plastics Guy. I'm your host, Kurt Stahle, That Plastics Guy. If you're new to the show, this is where I share my almost 4 decades of plastics industry experience with you. Today I'm on my own, but sometimes I have a guest, maybe even 2. I educate, share stories, showcase innovative products, and always discuss topics and trends that affect our industry. Today's podcast is sponsored, as always, by my company, Simcoe Plastics Limited, where we truly have a passion for polymers. You can visit us at the refreshing simcoeplastics.com or contact us at info@simcoeplastics.com. So what is water absorption? Well, water absorption is also called moisture absorption, and it's the capacity of a polymer to literally absorb moisture from the environment into the polymer structure. Absorbed moisture acts as a plasticizer of kinds. So it reduces the glass transition temperature and the strength of plastic. While it is certainly a reversible effect, the prolonged absorption of water can also lead to irreversible degradation of the polymer structure. So water absorption is expressed in an increase in the weight percent or percent weight gain of a plastic specimen. And that can be expressed in a very simple, actually, mathematical equation. The wet weight of the plastic in a controlled measurement, perhaps the part itself, the wet weight minus the conditioned weight divided by the conditioned weight times 100 to get a percent. So it's essentially the change over the original, the delta divided by the original weight. So it's a pretty standard calculation for calculating the percentage change of just about anything you're trying to measure. So how do we test for water absorption? Well, we're going to do just a quick rundown, then we'll get into test methodology a little bit later on in the show. Water absorption, 24-hour period at 23 Celsius, immersion of the plastic specimen in distilled water for 24 hours at 23 Celsius. So that's, basically room temperature, unless you're like me and I like to keep my house at 21 or even 20, even during the winter. But enough about me. Water absorption, 24 hours at 100 Celsius, so boiling. Immersion of a plastic specimen in distilled boiling water for 24 hours. Next, we have water absorption at saturation. Immersion of the same plastic specimen in distilled water at room temperature, 23 Celsius, and the measurement occurs when the polymer does not absorb water anymore. So what is the maximum amount of water that can be absorbed into a polymer that you're trying to test? So this test, I'm going to assume, has no time limit whatsoever, but I'm sure the specimen would be checked periodically. And lastly, water absorption at equilibrium. And the plastic specimen is exposed to a humid environment, typically at 50% relative humidity, at a specified temperature, room 23 Celsius, for 24 hours. The equilibrium moisture content can be used to compare the amount of water absorbed by different types of plastics when they are exposed to moisture. So we have a bit of a measuring bar there. And what does water absorption do to polymers? And I think we're going to be familiar with probably most of this. So we have dimensional and mass changes, so typically swelling caused by water absorption. The extraction of water-soluble components. So if you have elements within the polymer matrix that can leach to the surface or are water-soluble, maybe, I'm not sure if fillers are typically encapsulated, but if you have another type of additive, perhaps an integral lubricant package, that can be drawn to the surface and essentially taken away. And changes in mechanical properties, so elasticity, tensile strength, impact strength, and electrical performance. And I'll get to that a little bit further along in the show. Exposure to humidity Immersion and exposure to boiling water can result in distinctly different material responses, depending on the material that is encountering moisture. And some materials will have virtually no response, and we'll touch on that too. So how does water absorption change the processing and properties of the material? So the water absorption data is important to understand for the performance of the polymers during processing. For example, to avoid premature moisture-related failures during injection molding in water-rich or humid environments. And I think, in terms of most people's experience, nylon is going to be the one they have to be very, very careful with. Injection molding a damp, humid, moist, whatever the case, nylon is not ideal. You're going to have cosmetic defects, which we'll touch on a little bit more. You have to dry the nylon prior to molding, but you're not going to be able to assess or address physical property characteristics of the part until it's been back into relative humidity, normal relative humidity, and can reabsorb some amount of moisture to get the characteristics it needs. Nylon is a bit unique. Polyurethane, I believe, falls into that same category. The absorption phenomenon is particularly detrimental to plastic products. Yes, we know this. The wet material is also more permeable to gases. For example, a wet or damp nylon 6 has CO2 permeability 3 times greater than when it's dried. So I do want to just touch again. The permeability may increase, but we also need the nylon to have absorbed regular ambient moisture in order for it to get to its conditioned state where physical properties are optimal. Not super heavy, laden with moisture, not dried. You have to have a regular level of moisture for nylon to have its maximum characteristics, and typically you'll see that on the data sheets as to how they condition it. So in the presence of moisture, the material structure will tend to decrease thermal insulation. And just to think about that for a second, if you're dealing with a damp material of any kind, you're going to feel hot and cold through it relatively more, and can increase dielectric properties because water is in fact a conductive agent. The absorption and the presence of moisture in the polymer structure is one of the factors that will cause premature aging in the material. Yes, you can get, I'm not going to say waterlogged material, but for material that's specifically hydroscopic, you are going to have problems with that material degrading more rapidly than if it were kept in its proper environment, assuming it's not intended to come in contact with water. And that leads me to my next point. Polyolefins, polypropylene, polyethylene, contain no chemical bonds that are easily influenced by water or hydrolyzable. There you go. There's the word of the day, hydrolyzable. Hence, they absorb little water and essentially are unaffected by aging in water. And of course, that's why we see polyethylene specifically in blow molding applications used for transporting household cleaning products, motor oil, basically everything that you see at a typical department store, polyethylene blow molded, and it just doesn't seem to be affected at all by any contact with liquid. That, in fact, it's got excellent chemical resistance. When you have moisture present, that reduces the viscosity of the plastic, making it easier to flow. So remember, viscosity, the idea of viscosity, if it reduces viscosity, flow is higher. If viscosity is raised, flow is lower. So the two sort of have this inverse relationship when you're thinking of them. So when you have flow that's higher than anticipated, naturally you're going to have some processing issues because you're setting up for one type of material and it's responding in a different manner. So you could have excess flash, for example. And moisture in the material also affects the appearance of the part, and we've all seen splay, what we call the splay, that type of silver, tiger striping is something else, but that silver marking, and it's very common to emanate from the gate of the part, and it looks like, well, silver fireworks. So that's moisture in the material, and it's really the first sign that you're dealing with something that hasn't been properly dried or should be dried if it's not typically dried. So, for example, if an injection molding process uses wet material, the plasticization stage, the heating of that material, you're going to have a reaction occurring in the screw and barrel, and you're going to basically force the material to change as the water is pressurized through. And again, that's going to give you your splay as well as the deterioration of the mechanical properties. So wet material in the screw and barrel, that's where the problems start. Keep moisture out of the screw and barrel. Only push the plastic. Don't push anything else. So the use of moist acrylic material, for example, in injection molding, causes the matured parts to have poor surface quality. Wet acetal, that can lead to changes in dimensions, for example. PET and PBT materials, can lead to shorter chain molecules present in the hydrolytic decomposition, which results in a significant deterioration in the mechanical properties of material. And of course, in nylon, I've mentioned the presence of moisture really impairs the impact strength and the mechanical strength, and you have to let the parts recondition. I'm sure many of you who are in injection molding, and I'm sure that's most of you who are listening, if you've run nylon and you don't have much time in your shoot and ship environment, for example, you'll put freshly molded nylon parts into a Gaylord container lined with plastic, filled with water, and you anneal the parts. You're forcing that water uptake to maximize the time it takes to get the nylon part to reach its ideal physical properties. So some polymers, they have a natural tendency to absorb water, hygroscopic. Indeed, these superabsorbent polymers are gaining traction in advanced medical and construction applications. However, at the same time, the absorption capacity of thermoplastics can lead to changes in the physical property characteristics. So how do we measure water absorption? So the most widely used is ASTM D570 and its equivalent ISO 62. So in ASTM D570, the standard method for water absorption of plastics, and really the test has two chief functions. It's a guide to the proportion of water absorbed by the material, so it's something that we can quantify. And in those cases where the relationship between moisture and electrical or mechanical properties or dimensions exist, we have to be able to have a way of measuring that. And the follow-up, it's a guide to the effects of the exposure to water or humidity on those such properties. Again, it comes back to having to quantify key properties of the materials. And then secondly, it's a control test on the uniformity of a product, and it's particularly applicable to sheet, rod, and tube arms when the test is made on the finished product. So water absorption, it's a method of quality control to ensure the material as it's made is made in a uniform manner. And there are a lot of quality control checks. Again, you look at a typical data sheet, those are all quality control checks, specifications held by the material manufacturer. So the actual test procedure, the specimens are dried in an oven for a specified time and temperature, which will be denoted on the data sheet if there's something unusual there. And we want to get all of the moisture out of the material, so it's a dried state. So they're placed in a device to cool, and immediately upon cooling, not allowing to have moisture reabsorb in. We just want to bring the plastic down to room temperature. The specimens are weighed. The material is then immersed in water conditions, as I described at the top of the podcast, typically at room temperature, 23 Celsius, for 24 hours or until a state of equilibrium is reached. The specimens are removed, patted dry with a lint-free cloth, and weighed. So in ISO 62, we are measuring moisture absorption properties through the thickness, direction of flat or curved form solid plastics, and the amount of water absorbed by the plastic specimens of defined dimensions when immersed in water or subjected to humid air under controlled conditions. Now, this podcast is going to be a little bit on the shorter side, but I'm going to just conclude this with going through, it's actually quite a detailed chart courtesy of Omnexus, and I really just want to illustrate some of the materials that have the maximum amounts of weight gain through moisture, through absorption, just to give you an idea. Now, these values are expressed in percentage. It's still a low percentage of the overall material, but I just want to simply illustrate the potential for certain materials to absorb moisture. So ABS, something that just about every shop deals in, minimum value 0.05 of a percent, 0.5%. Its maximum or equilibrium water weight value 1.8%. So that is a significant increase in moisture, a significant increase in the take-up rate of moisture, and I think you can understand how that much moisture, which is essentially a foreign element in the processing, how that can really be quite disruptive to the physical appearance as well as the physical property characteristics. Now I'm going to go past some of the styrenics. I want to get to a few other things that we may encounter on a regular basis. Okay, so here's another one. This is a material that really is not absorbing moisture tremendously, but I'm just going to give you this data to make the point. EVA, ethylene vinyl acetate, its dry state, 0.005 of a percent of moisture, max moisture, 0.13. So it's not a significant increase in moisture. Well, maybe in terms of a percentage change, it's still significant, but overall, 0.13 of a percent max weight. You could probably still work with the material, and you wouldn't have to necessarily dry it pre-processing unless it was a particularly humid day and you just want to have all your potential quality control checks in place, all your processing checks in place, and you run it through a dryer at a mild temperature to remove some surface moisture. Here we go. High density polyethylene. So we talked about polyethylene and polypropylene not being too bothered by moisture at all. Its dry state 0.005, just like EVA. Its equilibrium 0.01. So it's very, very little moisture absorption. And again, running it through a hot air dryer on a particularly humid day, I'm thinking southern United States or Ontario on the worst days. Run it through a hot air dryer, knock that surface moisture off, and you're just guaranteeing that you will be able to process a great part. High impact polystyrene, dry weight 0.05 of a percent, maximum, the equilibrium maximum moisture content 0.15 of a percent. So it's still very little. Could that cause you problems again on those ultra humid days? Yeah, absolutely could. Now I want to get through to some of the nylons. Yeah, here we go. Nylon 6,6, 30% glass fiber. So this would be a pretty typical grade that you'd see in an automotive molding shop. Dry weight percentage, 0.8 of a percent. Moisture content maxes out at 1.1%. Doesn't sound like an awful lot, but with nylon, it's hygroscopic, and that water absorption is going to cause much more inconvenience to you than some of the other polymers. Let's see, pick out a couple of other ones. Here's one. Okay, another one that's very common and susceptible to moisture uptake, polycarbonate. Dry percentage of moisture, 0.1 of a percent, and that rises to 0.2 of a percent. But we know when we try and mold wet polycarbonate, we get splay. We can even hear the moisture crackle as it's injected, or if you're doing a purge from the screw and barrel when it's retracted, You can hear the snap, crackle, pop of the moisture in the material. You don't want that. And, again, it doesn't sound like it's a significant increase in weight, or percentage rather, but there you go. That small percentage can have incredibly detrimental effects on the material when you're trying to mold it. Just looking through a couple of other things, 30% glass-filled PET, another sort of common material for maybe under hood automotive applications. Dry moisture percent, 0.05, maxes out at 0.1%. It's still enough to cause problems. So when you're dealing with hydroscopic materials, I'm repeating myself, dry them, dry them, dry them. and you're setting yourself up for success. Let's see, I want to look at polypropylene, either homopolymer or copolymer, unfilled. The dry percentage of moisture, 0.01, so very, very low, maxes out at 0.1%. So percentage-wise, it looks like a big number, but in terms of that particular resin, it does virtually nothing to the physical properties. Again, if you have the humid day, run it through a hot air dryer on top of your machine just to knock off surface moisture, and you'll increase the odds of having that cosmetically perfect part. And I wonder if there's anything else that... No, not too much there. I think the last one I'm going to give you, your typical GPPS, crystal polystyrene, the dry moisture level, 0.01%, maxes out at 0.04%. Again, doesn't sound like a big deal, but if you want to increase your success of having that perfectly cosmetic part, reduce your problems molding, hot air dryer on top of the machine would be a very, very good option. Oh, here's one. Now, I don't deal with a lot of rigid PVC. That's typically producer direct business. The dry moisture percentage, 0.04%. It can max out to 0.4%. So that's a pretty significant increase. And you tell me, for those people out there running rigid PVC, you drying this material? I would think you would be. But I just wanted to show you what can be done there. One last one. Cross-linked polyethylene, typically used for rotational molded kayaks, canoes, that type of thing. Very, very durable material. The dry moisture content, 0.005%, and it maxes at 0.01%. Again, just showing you it's a resin that is not affected by moisture content. And obviously, if you're making a boat out of it, you don't want it to be impacted by water. So that's really all I wanted to talk about with respect to the impact of moisture on resins. And I hope you enjoyed it and were able to get a few nuggets out of what I've talked about. Again, go to Omnexus and you could check out the information there at your leisure. But I think that's a really great site for finding all things plastic. So, I always leave the invitation open. Drop me a line at the Plastics Guy, the group on LinkedIn, and let me know what you think of the show. I'm always open to topics for a show. I've done shows based on input from folks on the Plastics Guy group. I always watch, so let me know what you think. Give me a suggestion. You can follow Simcoe Plastics on Facebook, Instagram, and YouTube, and I'm on LinkedIn personally as Kurt Stahle. Please subscribe to our newsletter. You can do that through the website, easy to follow link, and we'll have an October letter out. Yeah, I think probably by mid-October. My genius office manager and graphic designer extraordinaire is on a vacation at the moment, but I'm sure when she's back, we'll get that done. And I really love what she does. I hope you do too if you're subscribing. We try and make it not only informative, but visually attractive for you as well. So that's it. Thanks for listening. Take care, and we'll talk to you again in another couple of weeks. Bye-bye.